Hello everyone, let's understand reflection of light using wave theory. Even in this case, we will assume a plane wave. As shown in diagram, let us consider a boundary called as PQ, and here the wave falling is a plane wave. Let's draw a better diagram to make more sense out of it. Let's take a boundary called as P and then Q. Since it is a reflective medium, let us represent it by a silver surface or a polished surface. Let's take a plane wavefront incident an angle inclined an angle to the normal. Let's call this as the incident wavefront, which is A. This is point B. This is point A dash. This is point B dash. And this would reflect and go like this. It reflects and goes like this. It goes like this, which means every point on this acts like a source, producing secondary wavelets. It goes like this. Even here, it's still traveling. This also travels. This travels from here to the surface. Even this would produce a secondary wavelets. By the time it comes to this point B has gone somewhere. Think that point B has gone to some point till some point here. So it is producing secondary wavelets, and even this would reflect and form secondary wavelets. So common tangent drawn from here to here. This would indicate the reflected wavefront. So this part here is the incident wavefront, and this part here, the common tangent drawn here, this part would be the reflected wavefront. So the incident wavefront is plane, and also the reflected wavefront is plane only. This is what we get when we draw the common tangents. Now to prove the equation, let's consider a case where we have a plane wavefront. In this case, let's draw only the edges of the wavefront, not the common tangents. Suppose we have a wavefront incident angle to this one. Let's call this as point A, point B, point A dash, and point B dash. This part here, it is the whole part. We get common tangent everywhere here. This is what the common tangents are. That is, what I meant here is, if you have a wavelet here, the wavelet here also, the wavelet here, the wavelet here, the common tangents. This is called as incident wavefront. Again here, there are two laws of reflection. The first law is based on observation, which can be proved here. So we just need to prove the second law. The second law says that the angle of incidence is equal to the angle of reflection R. We need to prove this law first. So light reflects and goes like this. We draw normal at this point. This would be I, and this should be R. This is the point B somewhere here. By the time the point B dash comes to the interface, come to the boundary, let's call this point C. The energy from the point B, or the wave from point B, has gone to some point here. Common tangent drawn from here to here. This is a common tangent. So it would go like this. This also goes like this. So this part is this part here, let's call this point as point D. So this whole part would be the reflected wavefront. Let's not draw the common tangents, let's draw only the edges of the wavefront. This part is called as reflected wavefront. Let's assume that it's in a medium where the speed here is taken as v. If it's air, then the speed becomes c. Let's take a general medium v. Now the angle made here is 90 degrees, it's a common tangent. Similarly, the angle made here is 90 degrees because bb dash is a common tangent. If this angle is I, even this should be I. It's already proved in a previous lecture. Go back and check it if you don't understand how it is y. Now this angle is r. This whole angle should be 90 degrees because n dash is normal to the surface PQ. If this is angle r, that is, if the angle between the normal and BD is r, then this angle here should be 90 minus r. For the triangle BD and C, first triangle BDC, I'll highlight the triangle. This angle here is 90. This angle here is 90, and this angle here is 90 minus r. Should be r. And also the distance, in this case, distance b dash c is same as b into d. That is same as vt, because by the time the point b dash comes to point c, the point b has gone to point d. So let's find out the second law here. From triangle, let's look at triangle b dash c. From triangle, let's find out what is sine I. This is the angle made here. It is triangle b dash c, which is this triangle. I'll highlight with a green color. This is triangle. From here, sine I is equal to, it will be b dash c by the hypotenuse, which is BC. The same as VT by BC. From triangle BDC, what you get from here is sine R. Sine R is equal to BD. This is what is the opposite side, which is BD, by the hypotenuse, which is BC, but BD is same as VT by BC. Now if you compare the two equations, let's call this as 1, this as 2. If we compare 1 and 2, it is very obvious that from 1 and 2, sine I is equal to sine R. This implies that I is equal to R. There is no need to use general trigonometric functions here. That is because the value of I and R is between 0 to 90 degrees. That's the range of it. For this range of I and R, the only possibility is when sine I is equal to sine R, it implies that I is equal to R. This is nothing but the second law of reflection. Therefore, by proving the second law of reflection, we have proved that even wave theory can explain reflection, which means wave theory is a consistent theory and a useful theory.